Here is the next example in Jordan form. So the given transfer function or mathematical equation is y double dot plus 3y dot plus 2y equal to u double dot plus 7u dot plus 12u. So here he's asking about find the state equation, output equation for the given mathematical model. So first thing, we're going to convert the given mathematical model into S domain. So it is s square y plus 3sy plus 2y equal to s square u plus 7su plus 12u. Okay, y by u, which is a transfer function, s square plus 7s plus 12 divided by s square plus 3s plus 2. Now the important point here is this system, this transfer function has two poles and two zeros. So if a system has two poles and two zeros, you cannot do the partial fraction. So first thing we need to do the partial fraction, number of zeros must be less than number of poles. Okay, so what we're going to do, I'm going to do the long division. So when I do the long division, s square plus 7s plus 12, s square plus 3s plus 2. So when I do the long division, 1, it's going to be s square plus 3s plus 2. I will end up with 4s plus 10. Okay, so y by u, I can write this as 1 plus 4s plus 10 over s square plus 3s plus 2. That's how. Now it has less number of zeros compared to poles. Now I can do the partial fraction. That's one important point we need to learn, or we learned from this example. Now I'm going to use partial fraction. So 4s plus 10 over, can I write this as s plus 2 times s plus 1? Okay, it's s plus 2 times s plus 1. Now I'm going to do the partial fraction. 1 plus a over s plus 2 or s plus 1 plus b over s plus 2. Now find a value and b value. A equal to, I can use the substitution method since there are no repeated poles. 4s plus 10 over s plus 2, substitute s equal to minus 1. So minus 4 plus 10 minus 1 plus 2. So 6 over 1, so it's 6. A equal to 6. Same way, b equal to 4s plus 10 over s plus 1, substitute s equal to minus 2. So minus 8 plus 10 over minus 1. So 2 over minus 1, which is minus 2. B equal to minus 2. Now y by u equal to 1 plus 6 over s plus 1 minus 2 over s plus 2. Okay, so what I'm going to do now, we know that 1 over s plus 1, I can draw a simulation diagram for that. So the simulation diagram for that is 1 over s. So I have plus 1, so this must be negative feedback, and 1 over s, so I have plus 2, so that must be negative 2. Okay, now here is u and here is y. Okay, when it comes to the y plus 6, it's, as I mentioned, these constants you can add them on the input side, or you can add them at the output side. I'm going to do the input side. So that is 6, that's positive, that is, it's up to you, you can put minus 2 or plus 2. Okay, that's u. Since the constants I took to the numerator side, or sorry, I took it to the input side, I don't need to add them here. Now I have 1 plus, so basically 1 is nothing but y and u directly connected. Okay, so that's the, I think we had similar example in either controllable canonical form or observable canonical form. Okay, so here you can clearly see there is a direct relation between the input and output. So whenever you have number of zeros equal to number of poles, then there is always a direct relation between the input and output. So it's kind of emergency switch. When I press the emergency switch, immediately the system is going to stop, no matter what's going on the other side. So this is such kind of system. Okay, so we have two integrators, so two state variables, or we have two poles, you can say two state variables, x1 dot, x2 dot. Okay, so x1 dot equal to minus x1 plus 6u, and x2 dot equal to minus 2x2 plus or minus 2u, and then y equal to x1 plus x2 plus u. So if you look at the A matrix, as I mentioned, in Jordan form you always end up with the diagonal matrix unless if you have a repeated pole, and B equal to 6 minus 2, and C equal to 1 1, and D equal to 1. So if you have a D matrix, you can clearly tell the number of poles are equal to number of zeros, and there's a direct relation between the input and output. I will solve one more example in this video. So here is the next example: y double dot plus 4y dot plus 4y equal to u dot plus 2u. Okay, so when you convert this into S domain, s square plus 4s plus 4 times y equal to s plus 2 times u. So y by u equal to s plus 2 divided by s plus 2 square, isn't it? S square plus 4s plus 4 is nothing but s plus 2 whole square. Now I have repeated pole. At the same time I have pole zero cancellation in this example. If I cancel the pole zero in this case, what happened? I will end up with 1 over s plus 2, right? Now this transfer function is going to represent an entirely different system. Okay, here whoever end up with this mathematical equation, they have two state variables. When you cancel them, you end up with only one state variable. Okay, so never ever transfer pole zeros in this transfer function, because this system, once you cancel it, the new system is going to represent entirely different system than existing system. So do not do that. So since I have my repeated poles, I can say y by u equal to a over s plus 2 plus b over s plus 2 whole square. So you can find a and b values. So if I find b, basically b equal to, or I'm going to do the LCM method, a times s plus 2 plus b times plus b. Okay, so the denominators are same, so numerators must be equal. Okay, so I have s term a, okay, and there is 1, so a equal to 1, and b, so I have constant 2 on one side, 2a plus b equal to 2. Based on this, I can tell b equal to 0. So the y by u transfer function equal to 1 over s plus 2 plus 0 over s plus 2 whole square. Now, as mentioned, if you have a repeated pole, you're going to do a series block diagram. Okay, so it's going to have each one of them is going to have one feedback, 1 over s, that's going to be s plus 2, so for sure that's going to be negative feedback, minus 2, and another one is right here. That is also negative feedback. Now this is y, this is u, right? So to get y, u has to pass through one integral, I mean, or 1 over s. So this is right. Let me redo it, because the constant here is 1, so it's up to you. You can put the constant 1, or you don't need to do that. So when it comes here, this constant is 0, but it is passing through two integrals. Okay, so you must multiply that with 0. So here is your u. Now I have two state variables, x1 dot, x2 dot. So what is my x1 dot? X1 dot equal to minus 2x1 plus u, and x2 dot equal to minus 2x2 plus 0u. Okay, and y equal to x1. So basically I'll end up with minus 2 0 0 minus 2. That's my a, and b equal to 1 0, and c equal to 1 0, and g equal to 0. Okay, so if you have a repeated pole and pole zero cancellation, the important thing we learned, it will never ever cancel the pole zero. Okay, I will stop this example or this video here. I'll start with a new example in the new video. Thank you.